Hello guys, in the previous lesson we have built the whole estimator model with the real system dynamics, and so we have obtained the proper or estimated A and B value, which are indicating the system parameters of our real system dynamics. In a real life application, the real system dynamics is present, but in our microprocessors or the computer architectures, we have a software like the estimator model. And so if we have this kind of system or system dynamic, and then we can create a hat or a estimated or b estimated value in order to what? In order to obtain the proper values of the A and B. But in the last lesson we have a problem, okay? And so I should run our code like this one, and so the real value of A is equal to the 1, but in this case the A goes to what? The minus values, and so is around to what? Is around to 0.2 and 0.4. Between two values, and so we have an estimation, and so estimation error is given with the what? With this notation, okay? And so these are highly huge small values at this moment. And so how can we say this estimator model is okay or not? And so in the B we have this kind of information in here, and in A we have this kind of estimated values, but the error goes to 0. And then what? We conclude that we may have the proper or the exact values of A and B in a linear system, but if there is one condition satisfying that this A and B value should be given with the similar or closest values of these things, or the equilibrium point, okay? And so if we have the z dot value in here like this one, we should select the 0 0 0 and the r state x hat, a hat and b hat value, okay? But if I select this 0 value, or assume that we know that the a is around the what? The 0.9, okay, and b is around to 0.8. we can obtain these values because for example, if we have the mass spring damping ratio or the damping system in our real life, we can estimate or we can execute some mass value as an estimation value, for example 1 or 2.5 kilograms, okay? And so if we put the closest values or equilibrium value on the A hat and B hat value, this result is changed, okay? And so if I run this code again, and then the R system goes to what? Goes to error to 0, and error values or the A hat value is equal to the what? This value, okay? This highly small value, okay? But in the B value we have the 0.A is equal to the what? The 0.95, and so this closest value on the what? On the 1, okay? And so in the A value we have this kind of dynamics in here, but in the what? The 0.9, okay? And so if I run this code until the what? 100 seconds, or if I have more samples about the system, and so we have this kind of dynamics in here like this one, okay? And then if I have initial condition with the equilibrium points, and so we have more correct and observable proper values of the system parameters, such as the A and B, okay? And as well as this value is around the what? This notation, okay? And so also we have the two parameters in here like this one, AM and gamma value, okay? And so if I select this function like this one, and so if I select this function also in here in order to show the performance of these codes, and then also we have this notation. And so how the dynamics affected by changing the AM stabilizer value and the learning rate gamma value. Firstly, AM is smaller than these things, and so if I run this code, and so our dynamics is much more learning rate in here, or we cannot stabilize easily these things. And so these oscillation terms coming from the what? The stabilization terms, okay? And so if I increase the AM value, stabilization value, which is given by the x hat dot is equal to minus AM times x hat, and so if I run this code, and so this code is run on the what? On the more stable values in here, okay? And so if I increase the gamma value in here like this one, and so we have the more proper dynamics in here, okay? And so if I increase the 10 times the gamma value in here like this one, if I run this code, and so our proper code is more stable than before, because the 1.1 is reached at this moment like this one. And so if the stabilization term is increased in here like this one, and then the R terms is equal to the what? Is equal to the these things, okay? And so what happens if I change the values of the B? 9.0.9, 0.9, okay? And so if I run this code again, and then the R proper dynamics is given in the what? In the between the 0.9 and 0.94, okay? And so in the A dynamics we have the similar effect on these diagrams. And so error is goes to the what? That goes to the 0 value. And if we have the another diagram, 1.1 and 1.1 is higher than the 1 value in here, and so if I run this code, and so the R proper model is given at this moment, okay? And so also we have this information. The sinusoidal signal is used to what? Used to create the proper input value in here. But what happens if we remove the sinusoidal effect on this code? If I run this code again, and so our proper value is limited within this range, and so we have no terms with the what? With the learning ratio or learning rate cannot be utilized to what? To approach or closest to the what? To the real value. And so if we have this kind of systems, we should give the system the many different kind of inputs, which means that if we have the x value in here, and so we stimulate the whole system by input values with the what? With the many different version of it, and then we can have the more observable form or the more accurate results from the what? From the A and B value in the estimated model, okay? But we don't need to get the exact proper values of A in order to control or proper control of this system. And so in the next lesson we will create some feedback initialization controller approach in order to what? In order to reference or provide reference tracking approach on this system. And so how can we create, or how can we use the estimator model in order to what? In order to design the proper controller system. In this situation, or in the absence of the knowledge of the A and B or system parameters model in the equation of motion. Okay?